What is a transistor and how does transistor work in electronics? A transistor is a semiconductor device that is commonly used as an electronic switch or amplifier. It is a fundamental building block of modern electronics and is responsible for the operation of various electronic devices. There are several types of transistors, including bipolar junction transistor, BJT. This type of transistor has 3 layers of semiconductor material. The 3 common configurations of BJT are NPN, negative positive negative, and PNP, positive negative positive. BJTs are often used for amplification and switching purposes. A bipolar junction transistor, BJT, is a 3-layer semiconductor device consisting of 2 types of semiconductor material, either NPN or PNP. It is called a bipolar transistor because it relies on both electron and hole currents for its operation. The 3 layers of a BJT are the emitter, base, and collector. The emitter is heavily doped, the base is lightly doped, and the collector is moderately doped. The 2 junctions between these layers are the base emitter junction, B, and the base collector junction, BC. The BJT has 3 different operating modes. Active mode. In the active mode, the transistor is biased to allow current flow from the emitter to the base. The amount of current flowing through the base controls the larger current flow from the collector to the emitter. This mode is commonly used for amplification purposes. Cutoff mode. In the cutoff mode, the transistor is biased so that no current flows between the collector and emitter. It is effectively off and does not conduct current. Saturation mode. In the saturation mode, the transistor is biased to allow maximum current flow between the collector and emitter. It is fully on and acts as a closed switch. BJTs are widely used in various electronic applications, including amplifiers, switches, oscillators, and digital logic circuits. They offer good linearity, high gain, and fast switching speeds. However, they may require more power and have lower input impedance compared to other types of transistors like MOSFETs. It's important to note that BJT technology has been widely used for several decades, but in recent years, MOSFETs and other semiconductor technologies have gained more popularity due to their improved performance characteristics and lower power consumption. A field effect transistor, FET, is a type of transistor that relies on an electric field to control the flow of current. Unlike a bipolar junction transistor, BJT, that uses both electrons and holes for conduction, FETs are voltage-controlled devices and primarily use either majority carriers, electrons or holes, for conduction. There are 2 main types of FETs. Junction field effect transistor, JFET. JFETs are formed by creating a PN junction between 2 differently doped regions in a semiconductor material. The 3 common configurations of JFETs are N-channel and P-channel. In an N-channel JFET, an electric field created by a voltage applied between the gate and the source controls the flow of electrons through a narrow channel. Similarly, in a P-channel JFET, the electric field controls the flow of holes. JFETs are typically used in low-power applications and as voltage-controlled resistors. Metal oxide semiconductor field effect transistor, MOSFET. MOSFETs are the most widely used type of FET. They consist of a metal gate electrode separated from the semiconductor channel by a thin insulating layer, typically silicon dioxide. MOSFETs are further categorized into 2 types, enhancement mode and depletion mode. Enhancement mode MOSFET. In an enhancement mode MOSFET, no conducting channel exists between the source and drain regions when there is no applied voltage to the gate. Applying a positive voltage to the gate creates an electric field that attracts majority carriers, either electrons or holes, to form a conducting channel. Enhancement mode MOSFETs are commonly used in digital logic circuits and amplifiers. Depletion mode MOSFET. In a depletion mode MOSFET, a conducting channel is already present between the source and drain when there is no applied voltage to the gate. Applying a negative voltage to the gate depletes the carriers, narrowing or closing the channel, and reducing the current flow. Depletion mode MOSFETs are used in specialized applications such as voltage references and current sources. FETs have several advantages over BJTs, including high input impedance, low power consumption, fast switching speeds, and better temperature stability. These characteristics make FETs well-suited for applications such as amplifiers, analog switches, power electronics, and integrated circuits. MOSFETs, in particular, have become the dominant transistor technology due to their scalability and compatibility with CMOS, complementary metal oxide semiconductor, processes used in modern integrated circuits. Insulated gate bipolar transistor, IGBT. An insulated gate bipolar transistor, IGBT, is a type of transistor that combines the features of a bipolar junction transistor, BJT, and a metal oxide semiconductor field effect transistor, MOSFET. It is designed to handle high voltage and high current levels, making it suitable for power electronics applications. The structure of an IGBT consists of a heavily doped N+ substrate acting as the collector, a p-type base region, and an N+ region acting as the emitter. Between the gate and the base region, there is an insulating layer, usually made of silicon dioxide, and a metal gate electrode. The insulated gate allows for voltage control, similar to a MOSFET. The operation of an IGBT involves the following stages. Off state: when there is no voltage applied to the gate, the IGBT is in the off state, blocking the current flow between the collector and the emitter. Turn on: applying a positive voltage to the gate relative to the emitter allows a small current to flow into the base region. This current causes the base emitter junction to become forward biased, which injects holes into the N+ region and triggers the conductivity modulation effect. As a result, the IGBT turns on and allows a large current to flow between the collector and the emitter. On state: in the on state, the IGBT behaves like a low resistance switch, enabling the efficient flow of current with low voltage drop across it. It can handle high voltage and current levels with relatively low power losses. Turn off: to turn off the IGBT, a negative voltage is applied to the gate relative to the emitter. This causes the base emitter junction to become reverse biased, cutting off the current flow between the collector and the emitter. However, IGBTs have a relatively longer turn-off time compared to MOSFETs. IGBTs are commonly used in applications that require high voltage and current control, such as motor drives, inverters, power supplies, and renewable energy systems. They offer advantages such as high switching speed, low conduction losses, and good thermal stability. The combination of the voltage control of the gate, like a MOSFET, and the current carrying capability, like a BJT, makes IGBTs suitable for power electronics where high power handling is required. Darlington transistor. A Darlington transistor, also known as a Darlington pair, is a configuration of two bipolar junction transistors, BJTs, connected together to provide a high current gain. It is named after its inventor, Sidney Darlington. The Darlington configuration consists of two transistors, a driving transistor, usually a smaller signal NPN or PNP transistor, and a driven transistor, usually a larger signal NPN or PNP transistor. The emitter of the driving transistor is connected to the base of the driven transistor, and the collector of the driving transistor is connected to the base of the driven transistor. The primary purpose of the Darlington configuration is to achieve a very high current gain or current amplification factor. When a small input current is applied to the base of the driving transistor, it causes a larger current to flow through the base of the driven transistor. This amplified current is then used to control a larger current flow through the collector-emitter path of the driven transistor. The overall current gain of the Darlington pair is the product of the individual current gains of the driving and driven transistors. As a result, the Darlington configuration can provide very high current gain values, typically in the range of thousands or even tens of thousands. The advantages of using a Darlington transistor configuration include high current gain. The Darlington pair offers a significantly higher current gain than a single BJT, allowing for efficient amplification of small input currents. Increased input impedance. The input impedance of the Darlington configuration is higher compared to a single BJT, which makes it more suitable for driving loads with high impedance. Improved linearity. The use of two transistors in the Darlington configuration helps reduce nonlinear effects, leading to improved linearity in amplification. Higher power capability. The Darlington pair can handle higher power levels due to the increased current capability provided by the current gain. Darlington transistors are commonly used in applications that require high current amplification, such as power output stages of audio amplifiers, motor control circuits, relay driver circuits, and high current switching applications. It's worth noting that the Darlington configuration introduces a higher voltage drop between the collector and emitter compared to a single transistor due to the combined voltage drops of the two transistors. Therefore, it is important to consider the power dissipation and voltage requirements when using Darlington transistors. Thyristor. A thyristor is a family of semiconductor devices that are used as switches in power control applications. Thyristors are known for their ability to handle high voltage and current levels and their ability to conduct current in one direction once triggered. They are often used in applications that require the control of power flow, such as motor drives, lighting control, power supplies, and AC power control. The most common types of thyristors are silicon-controlled rectifier, SCR. The SCR is the most widely used type of thyristor. It consists of 4 layers of alternating p-type and n-type semiconductor material. The SCR can be turned on by applying a positive voltage pulse to the gate terminal relative to the cathode terminal. Once triggered, it remains conducting until the current flowing through it drops below a certain threshold, or until the voltage across it is reversed. Gate turn-off thyristor, GTO. The GTO thyristor is a type of thyristor that can be turned off by applying a negative voltage pulse to the gate terminal. This makes it more controllable compared to the SCR, as it allows for both turn-on and turn-off control. GTO thyristors are used in high-power applications where fast switching speeds and controllability are required. Triac. The Triac is a 3-terminal device that acts as a bidirectional switch. It can control the flow of current in both directions when triggered. Triacs are commonly used in AC power control applications, such as dimmers and motor speed controllers. Diac. The diac is a 2-terminal device that is used to trigger the triac. It is essentially a bidirectional diode that can conduct current in either direction when the voltage across it exceeds a certain threshold. Thyristors are known for their ability to handle high current levels and provide reliable switching in power control applications. They offer advantages such as high voltage capability, low control power requirements, and robust operation. However, it's important to note that once a thyristor is triggered, it remains conducting until the current through it drops below a certain level or the voltage across it is reversed. This non-latching behavior distinguishes thyristors from other types of electronic switches. It's also worth mentioning that with advancements in power semiconductor technology, other devices like insulated gate bipolar transistors, IGBTs, and power MOSFETs have gained popularity in certain applications due to their faster switching speeds and better controllability. Uni-junction transistor, UJT. A uni-junction transistor, UJT, is a 3-layer semiconductor device with only one junction. It is a unique type of transistor that operates as a voltage-controlled oscillator or a relaxation oscillator. The UJT is primarily used in timing circuits, pulse generators, and triggering applications. The structure of a UJT consists of a lightly doped N-type silicon bar, also known as the intrinsic region, with 2 heavily doped P-type regions at each end acting as the emitter and base terminals. The emitter terminal is connected to the intrinsic region near one end, while the base terminal is connected to the other end. The UJT does not have a collector terminal like other transistors. The operation of a UJT involves the following stages. Off state: when no voltage is applied to the emitter terminal, the UJT remains in the off state, and only a small leakage current flows from the base terminal. Peak point: as a positive voltage is applied to the emitter terminal, it creates a forward bias on the emitter base junction. This allows the base region to accumulate charge and creates a potential barrier at the intrinsic region near the emitter. When the voltage reaches a certain level, called the peak point voltage, VP, the UJT enters the peak point region. Valley point: as the emitter voltage continues to increase, the potential barrier at the intrinsic region decreases until it reaches a minimum value. This minimum value is known as the valley point voltage, VV. At the valley point, the UJT transitions to the on state. On state: in the on state, The UJT exhibits a low resistance between the emitter and the base terminals, allowing a large current to flow through the device. The UJT remains conducting until the emitter voltage decreases below the valley point voltage. The UJT acts as a voltage-controlled switch, where the timing and triggering characteristics are determined by the values of Vp and Vv. By controlling the timing of the on and off states, UJTs are used in applications like timing circuits, sawtooth waveform generators, voltage-controlled oscillators, and triggering devices for thyristors and SCRs. It's important to note that while UJTs were widely used in the past, their applications have become less common with advancements in integrated circuit technology and the availability of other types of devices. Nonetheless, UJTs still find occasional use in specific applications that require their unique characteristics.